In this video, we will learn how to perform the hypothesis test using z-test approach. A leasing firm claims that the mean number of miles driven annually, mu, in its leased cars is less than 13,060 miles. A random sample of 60 cars leased from this firm had a mean of 12,000 annual miles driven. It is known that the population standard deviation of the number of miles driven in cars from this firm is 3,320 miles. Is there support for the firm's claim at the 0.05 level of significance? Perform a one-tailed test, then fill in the table below. Carry your intermediate computations to at least 3 decimal places and round your responses as specified in the table. The claim of the leasing firm that I highlighted over here, the fact that their annual mileage they're saying is less than 13,060 miles on average, is what we are trying to find evidence for. This is the statement that will represent the alternative hypothesis. Please remember that the null hypothesis, h sub 0, is what we assume to be true unless proven otherwise. The alternative is what we are trying to prove. This is what we don't know yet, and we'll have to look at the data to decide if it's the case that h sub 0 still holds, or maybe we will have to accept the alternative to the null hypothesis. So when you read stories like that, I advise that you start by writing down the alternative hypothesis, which states that the mean annual mileage for the leasing fleet of this company is less than, that's their claim, 13,060 miles. Because the hypothesis test implies that there are only 2 alternatives, either h sub 0 is true or h sub 1 is true. Once you know the statement of the alternative hypothesis, the null hypothesis has no other choice but to say the opposite. So if alternative says mu is less than 13,060 miles, then a null hypothesis has to say mu is greater than or equal to 13,060 miles. Next, always state your alpha, the significance level. In this case, it is chosen for us to be at 5%. And now it is time to compute the test statistic, because that's the next thing we need to do according to the table above. First of all, you need to choose what kind of test statistics you have. Is it z, t, chi-squared, or p? Well, please notice that because we're working with means, and because we know the standard deviation, it is provided for us as 3,320, and because the sample size is large, even without assumption of normality of the population, we are safe to use the z-test. Therefore, it's time now to compute the test statistic z sub x bar. According to the central limit theorem, the formula for this value is x bar minus mu, where this mu is really the quantity we are using in the hypothesis, divided by the standard error, sigma over square root of n. So let's input the numbers we have. X bar is 12,000 minus mu of 13,060. Divide all of that by the standard deviation of 3,320 divided by square root of 60. When you input this into a calculator, please pay attention to the order of operations. To ensure the right order of operations, I recommend that you enclose the numerator in parentheses to ensure that that entire difference is divided by this quotient as well. So I would use parentheses around both of them when entering this computation into a calculator. The outcome is negative 2.473 rounded to 3 decimal places as requested above. Then the problem is asking for the p-value. What is a p-value? The p-value is the area with respect to the test statistic. Well, area in what direction? Well, it depends on the type of the test you have. So if you look above, I have a diagram of a standard normal curve with 5% of area shaded on the left. Why did I have that? I have it because I have alpha 5% and the alternative hypothesis determines the type of the test I have. This is a left tail test. So now I need to find out where is the z-statistic is and how much area it has to the left of itself. Why to the left? Because we have a left tail test. Well, the p-value is the area to the left of the test statistic. To compute this p-value, I can use the normal CDF function in my calculator and find the amount of area from negative infinity up to negative 2.473 with mean of 0 and 1 as a standard deviation for the standard normal curve. This produces the quantity you see here, 0.007. Notice what it means. It means that the negative 2.473 is somewhere right here, and the amount of area to the left of that quantity is equal to 0.007. Because the amount of area of 0.007 is less than the significance level alpha, here I state that, it means my test statistic lands in the rejection region and I need to reject the null hypothesis and therefore accept the alternative. Therefore, I can conclude and say, yes, the claim is correct based on the evidence we have. Miles driven annually for this company's leasing fleet is less than 13,060 miles. Now let's take a look how the same problem can be done using TI-84. First of all, I transfer the information from the previous page to make sure that I see everything I need to know, everything I'm given on this slide. So sample size is 60, sample mean is 12,000, population standard deviation is 3,320. Null hypothesis states that mu is greater than or equal to 13,060 miles. Alternative hypothesis, the claim we're trying to find evidence for, states that mu is less than 13,060 and alpha is 0.05. Now we're going to use this information and enter it into the TI-84. First we go to Stat and scroll to Tests. The test we need is the z-test, so the first one in the list. I have statistics, not the data, in raw format, so I'm going to use that option. Mu sub 0 is the quantity involved in the hypothesis statement, which is 13,060. Sigma 3,320. Sample mean 12,000. Sample size 60. This is a left tail test, which is defined by the alternative hypothesis inequality symbol. So I need to highlight less than and then go down to calculate. Once you press enter, you will get the results. As you can see, the z-value, the test statistic, and the p-value, when rounded to 3 decimal places, are exactly same as we found them to be on the previous slide when we did this manually. So you are welcome to use this test to perform hypothesis tests quicker instead of doing it with more computations in the manual format. Let's do another example. The mean SAT score in mathematics mu is 531. The standard deviation of these scores is 31. A special preparation course claims that its graduates will score higher on average than the mean score of 531. A random sample of 22 students completed the course and their mean SAT score in mathematics was 548. Assume that the population is normally distributed. At the 0.01 level of significance, can we conclude that the preparation course does what it claims? Assume that the standard deviation of the scores of course graduates is also 31. Perform a one-tail test, then fill in the table below. Carry the intermediate computations to at least 3 decimal places and round your responses as specified in the table. This example differs from the one we did previously in the method which we have to use to make a decision regarding the null and alternative hypotheses. What is the difference? The difference is that ALEKS is asking you to compute the test statistic, which we did in the previous example as well. So the test statistic will be z, and we will see how to compute the test statistic value. But it doesn't ask for p-value, it asks for the critical value, and then we're going to make a decision based on the relation between the test statistic and critical value. First, I suggest that we identify what we know. I know that sigma is 31, sample size n is 22, x bar for the sample mean, is 548. We are told that the population from which this sample is drawn is normally distributed, and we're asked to use alpha of 1%. Please notice it's very important with a small sample, which is less than 30 as you can see, to have a normally distributed population. Without the assumption of normality, we cannot proceed with this process with such a small sample. Now let's talk about the hypotheses. The claim is that after special preparation course, there's a claim that graduates of this course will score higher on the SAT score in mathematics on average, which means that my alternative hypothesis, for which we are hoping to find evidence, should say that mu is higher or greater than 531. The null hypothesis, therefore, must be mu is less than or equal to 531. So I stated it right here. Then I record my alpha of 1%. And the next thing that ALEKS is asking for is what type of test statistic it is. Well, because of the normality and because sigma is available, we're going to go with a z-test, and therefore z is my test statistic. Let's compute this test statistic. The test statistic z sub x bar, according to the central limit theorem, will be computed as follows: x bar minus mu over sigma divided by square root of n. In our specific case here, x bar is 548 minus mu, which is 531, the number to which we are comparing the sample data, 31 over square root of 22. When you enter this into a calculator, once more, I would like to remind you to be careful with the usage of parentheses. You have to guide your calculator on the order of operations you want it to use. So parentheses would be crucial here. Well, this quantity comes out to be 2.572. Now we need to find the critical value. Remember that critical value is depending on what your significance level is. In this case, alpha is 1%, and we have a right tail test. That's what this inequality symbol indicates. The greater than in the alternative hypothesis tells me I'm looking for evidence that my test statistic will be in the right tail. Let's see. So at alpha of 1%, I have 1% of area in the rejection region and 99% of area in the acceptance region. To find the point that separates these two regions, I need to use the inverse norm of z sub 0.01 that has 99% of area to the left of it, with 0 as standard mean and 1 as standard deviation for the standardized normal curve. The calculator would give you 2.326, so the point that separates critical region from acceptance region is 2.326. That's my z-score. Now, the test statistic we found previously is 2.572. Where is that quantity with respect to the critical value? Well, it's slightly bigger, so my test statistic ends up on the right side of the critical value, which means it's in the critical region, and for that reason, we're going to reject the null hypothesis and accept the alternative instead. So we have enough evidence at alpha equals to 0.01 significance level to conclude that the preparation course performs as claimed. Its graduates will score higher on average than the mean score of 531. This is our last example, and this is the example of a two-tailed test. A laboratory claims that the mean sodium level mu of a healthy adult is 143 milliequivalents per liter of blood. To test this claim, a random sample of 14 adult patients is evaluated. The mean sodium level for the sample is 135 milliequivalents per liter of blood. It is known that the population standard deviation of adult sodium levels is 11 milliequivalents. Assume that the population is normally distributed. Can we conclude at the 0.05 level of significance that the population mean adult sodium level differs from the claimed by the laboratory. Perform a two-tailed test, then fill in the table below. Carry your intermediate computations to at least 3 decimal places and round your responses as specified in the table. First of all, notice I highlighted the area that indicates the type of the test I have. I'm wondering, with the evidence I have, whether the sodium levels differ. So differ, it doesn't mean sodium levels are higher or lower, they're just different. That's why, for my alternative hypothesis, I'm using the not equal to symbol. Therefore, null hypothesis has to be the equal. I write them down right here. I list my alpha, which is provided for me in the text itself. And then ALEKS is asking for the type of statistic. Again, you have two choices here. Is it z-test or t-test? Those are the only two choices you may have when you are doing the test regarding the mean, mu. Well, notice the sample size is 14. It's quite small. However, sigma is known, and we're told that the sample is drawn from the normally distributed population, which allows me to use the z-test. So I'm working with test statistic of z. To compute the test statistic, z sub x bar, I'm using the same formula we used for the other two examples. Input the information. Your sample mean is 135 minus 143, the mean that is involved in the hypothesis statement, the mean to which we compare. And then divide that by standard deviation of 11 divided by square root of 14. This quantity comes out to be negative 2.721. This z-score is somewhere on the z scale, and it's hard to tell right now where exactly it is. To do that, first I need to find the p-value corresponding to this test statistic, z sub x bar. How do I do that? Remember, my z happens to be in the left tail. Well, maybe it's here, maybe it's here. It's hard to tell. I don't have a scale, right? But I need to know how much area it has to the left of it. And I do that by using the normal CDF between negative infinity and negative 2.721. So I'm trying to find the area from negative infinity up to, well, some location. I'm not certain where exactly it is visually, not yet. Once I compute this quantity, I have to double it. Now, why do I need to double it? The way this formula works, the way this setup works, because of a two-tailed test, in reality, I have a symmetric setup here, and this test statistic only has half of the area that I'm going to be comparing to alpha. Another half is symmetrically located in the right tail. So p-value must be twice the amount of area to the left of this negative 2.721. So once I double that quantity, I got 0.007, which really means only half of this quantity, or 0.0035, 35 10,000ths, is the amount of area to the left of negative 2.721. Well, my alpha is 5%, which means for two-tailed test, 2.5% of area is in the rejection region on the left, and 2.5% of area is in the rejection region on the right. Where is this amount of area divided by 2? How much is 35 10,000ths? Well, it's a very, very small quantity compared to the 25 thousandths. So I don't know, maybe it's this much area right there, and symmetrically on the other side right there. So these two areas combined together right here, 0.0035 or 35 10,000ths, and right here 0.0035 thousandths combined together gave me this p-value. Again, remember, if p-value happens to be less than or equal to 0.05, your alpha, you can go ahead and reject the null hypothesis. We're going to write that down, reject null hypothesis, which means alternative must be true. We're going to conclude yes, H sub 1, stating that mu is not equal to 143 is true. The population mean adult sodium level differs from the claimed by the laboratory at the 0.05 level of significance. Here is how we can do the same test again using TI-84. Go back to Stat, scroll to Tests, and choose the first option, Z-test. Again, we're going to enter our mean involved in the hypothesis, 143. Sigma is given to be 11. So we're going to enter 11 there. X bar is 135. Sample size is 14. I have to make sure that my two-tailed test is chosen, so I have to select and press enter to select the not equal to, and then press enter when you get down to calculate menu. And the result, as you can see, is the same. We got the same z value, the same p-value, and the same conclusion, because p-value of 0.007 is significantly smaller than the alpha of 0.05. We actually have strong evidence that the sodium levels are different from those claimed by the laboratory.